Thanks for joining us for the final Future States lecture for this series. Today we'll focus on a really interesting topic. I think everybody will find this very interesting. Sort of how the electric power industry is evolving and changing, and how Argonne's research plays into helping people think about that. So you've got the advent of natural gas hitting the scene in really a game-changing way, and how that all fits together with everything else that's going on with the grid, with electrification, et cetera, et cetera. And we have a very, very talented group of researchers here at the laboratory that think about that a lot. So you're going to hear from two of those today, and so I'm really looking forward to it. Specifically, the division that really is sort of the centerpiece for this work at the lab is the Decision and Information Sciences Division. It sits within Al Saddleberger's directorate. 165 staff members, really a wide range of sponsors that DIS works with. And we're lucky enough to have Dick Cirillo today here, the director of DIS, who will provide, I guess, the beginning of the presentation, then Guenter will step up and provide additional details. Dick's been at the lab for almost 40 years. I knew it was a long time, I didn't know it was almost 40 years. He's been director of the division DIS since 2006. And I should also say, this is an opportunity to say in public, Dick will be retiring very soon. I believe staying as an STA, which is important. Everybody needs to stay as an STA, because we don't like to lose people, especially talented people. But I want to publicly thank you, Dick, for all you've done for the laboratory and for the division. And so, thank you. So a little bit about DIS again. About 165 staff members, the portfolio about $55 million currently. And again, a wide range of capabilities: systems analysis, risk analysis, complex adaptive systems analysis, simulation and visualization. Again, working for a wide range of sponsors. And you'll hear more about that, I believe, from Dick, probably as an intro, and then on to Guenter. Dick himself has been actively involved in this research, addressing both energy challenges as well as homeland security related and national security challenges. Guenter Conzelmann, also of the DIS division, is the director of their Center for Energy, Environmental, and Economic Systems Analysis, a group that I'm familiar with and I've enjoyed working with over the years. Guenter focuses on, again, taking modeling and simulation and tools and applying it specifically to the energy system. So everything from the advent of renewables, wind power, and other renewables, thinking about how they fit into the grid, how transportation electrification fits into the grid, all the various questions you can imagine. Guenter's group has worked a lot in the U.S., but also with a lot of other countries as well. So I think you'll find this talk very interesting in terms of his thoughts on how things evolve here quickly on our energy landscape. So as we go through these dramatic changes, and again, you're going to hear a lot more about it, listen carefully, because I think a lot of what they're going to talk about is actually thinking about what the future is going to look like, and there's opportunities in here for the laboratory going forward to tease out some R&D opportunities, not only in the areas that these gentlemen work, but also how we can link together the broader parts of the lab to think about, say, the future energy system. So with that, the official title of the talk is The Convergence of Smart Grid, Renewables, Shale Gas, and Electric Vehicles. How can we sort it all out? And these gentlemen are about to tell us. So thank you.
Good. Okay, I'd like to start off by just giving you a little bit of background and a little context to this work. Argonne's got a long history in energy systems analysis. Started back in the late 60s, early 70s. At that time, the environment was becoming a priority national issue. There was the Clean Air Act, Clean Water Act, Endangered Species Act. All of these things were coming into play in the country. The lab decided that with its extensive background in doing systems analysis and in the development of commercial nuclear power, that there might be an opportunity for us to contribute some of that expertise to this newly emerging issue for the country. The lab made an investment at that time in a small group called the Center for Environmental Studies, We were housed over in the old Quonset huts in the east area, which is now an open field, those of you who may remember that. This group eventually was well positioned when the environment issue was complicated by the energy issue. The oil price shocks of 1973 and 78 again created a new national interest in how to deal with energy, how to look at the issues that we'd be facing in the future. And that group eventually merged into what was called the Energy and Environmental Systems Division. That division was the precursor of what is now the Decision and Information Sciences Division, the Energy Systems Division, and the Environmental Sciences Division. So the lab's investment in that small group has really blossomed over the years. Well, the work of that activity has taken on several dimensions now. The first part of what is done now is what we call develop. That is, develop state-of-the-art energy analysis tools. As we got into this issue of how to look at things from a systems perspective, we decided that a lot of the tools were not available, so we had to build our own. They were computer simulation models, databases, methodologies, things that could address the newly emerging issues. Then we were starting to apply those tools to critical energy issues. One of the first things that the laboratory got involved in was the Chicago residential coal ban. At that time, the city of Chicago was still burning coal in residential apartment buildings. We were the first ones to look at what the impacts of that would be, both on the environment and on energy. We got into more esoteric things like satellite power systems, the idea of putting solar cells up in orbit and beaming the energy back down to Earth via microwave. This was a joint project by DOE and NASA. We looked at the Illinois electricity market. What would happen when Illinois went to deregulation? And I have to say, at that point, we told the state, we told you so. We've been looking at hydropower, both conventional and advanced hydropower, and how that can contribute to the country's energy. We've looked at grid interconnections, a lot of international work, looking at Southeast Europe, looking in Asia, looking in Latin America at how various changes in the power grid can be implemented. And our third component, develop, apply, was to transfer our tools to other researchers. We've transferred a lot of the analysis tools and capabilities to countries all over the world, both in the form of training courses and collaborative studies and things that we've done for the World Bank, the U.S. Agency for International Development, and so on. And as you can see, we've got a pretty wide domain here, so we can truly say the sun never sets on the Argonne Empire. This is sort of the background of how we got to where we are today. And I'm going to ask Guenter to come up to give us some perspective on the new energy issues that are emerging and some of the things that we're doing to address those. Guenter?
So again, thank you everyone for being here today. I realize it's not quite as exciting as Obama speaking, so I definitely appreciate you coming, especially those of you from DIS. Special shout out. It seems like the email message from Dick Cirillo had an effect. It's the Sicilian subtleties, you know. So anyway, so here's a couple of points that I want you to take home as you leave, okay? So, and just in case as you zone out and you forgot by the time we're done, I will repeat them again at the end, okay? So the first one is really there's a lot of changes going on, a lot of substantial changes in this in the industry. And those changes really happen on both the supply side, in the way we generate power, as well as on the demand side and on the consumer side of the industry. And then in between, the transmission system as well as the distribution system. And it means things like it might change the way we consume power, how we consume electricity, what we consume electricity for, think of electric vehicles, and ways of enabling certain things that we can't do right now through the smart grid. Replacing regular meters with smart meters, allowing us to do things that we can't do right now. Now that opens up opportunities for certain technologies. A lot of those technologies have benefits and values, but they also introduce challenges. And I'll be talking about some of those challenges today. And what's clear, however, is as we move forward implementing some of those changes, the models that we have, the tools that we use, the approaches, the methods, the data that we use are really not going to be sufficient to fully really understand all the implications that these changes will have. So that's the key messages. So here's a reference point. How many power plants do you think we have in the country, across the country? How many power plants do you think? Anyone want to take a guess? Huh? 12,000. That's a pretty good one. 18,000. Okay? 18,000 spread around from small diesel generators to large nuclear power plants, large hydro plants, large coal plants. About over 1,000 coal plants, 1,400. Some of them are retiring fairly rapidly, introducing some of the challenging changes that we see. We have over 100 nuclear reactors. And then, of course, we have thousands of plants that use natural gas. And then a whole bunch of others that use geothermal, diesel, and whatnot. All right? So there's a lot of those. Now, those 18,000 power plants, they generate a lot of electricity. 4,000 terawatt hours. So if you think of your household, okay, so your home, the average household consumes about 10,000 kilowatt hours a year. All right, 10,000 kilowatt hours. This is 4 trillion kilowatt hours. So it's a lot of power. Okay? And as you can see, we use a lot. Right now, we still use a lot of coal. Okay? The large majority of this is coal, quarter from natural gas, and a fifth from nuclear, and the rest is sort of split up into renewables, a lot of renewables, mostly really hydropower, but also wind and solar, and others. So this is the current mix, but as we'll see as I go through my presentation, you'll see that this is changing rapidly. And it's changing from multiple fronts, okay? So there's hydropower and implications. Hydropower used to be a no-no, was ignored by DOE for many years, now it's back on the table. Can we get more power out of our existing hydropower dams? Can we even build new hydropower dams? Not here in Illinois, okay, but in other places, all right? Wind, and we'll see how quickly wind and solar is growing. And it's amazing the growth rates these resources see. Smart grid, what does that do? New consumers, electric vehicles. What if there will be millions of electric vehicles on the grid? Can the grid handle that? What are the implications of that? So a lot of changes, and since we're trying to do all of this at the same time, it almost feels like it's a perfect storm. Okay? And we don't really know the outcome quite yet. I'm not able to tell you exactly how it will play out. If you came here thinking that I have the crystal ball, being able to tell you what the future is going to be like, you'll be disappointed. Okay? I'm just here telling you, okay, here's some of the recent trends we see. Here's the problems that we have in terms of trying to understand it, and here's what we need to do to get a better handle on understanding as we move forward. Right? So that's the purpose of the talk. Right? So this is our system. Okay? So it's an interconnected, tightly coupled system. What does that mean? It means if I change one thing in one corner of the place, it changes everything else. It's tightly coupled because we can't store electricity. We have to generate it the moment we consume it. There's no inventory management, okay, with electricity, okay, like we do with oil and gas and with just about anything else. Anything else you buy, the industry that provides that product to you has an inventory management ability. Okay? There's places, warehouses where they store things. With electricity, we don't really have warehouses to store things. Okay? We're working on storage. We're now the storage hub, mostly for transportation purposes, but also for grid. So we're concerned about, as we move forward, do we need more storage? It's a big question. All right? So we start out with the generators at the bottom. And as we heard, there's 18,000 of those generating the power that we all consume. Then we ship it over 200,000 miles of high voltage transmission lines around the country to about 60,000 substations. And from those 60,000 substations, we ship it again over 3 million miles of distribution lines to the consumers. There's a lot of infrastructure out there. Okay? And again, I change one thing, it'll affect the other. Okay? So tightly coupled. And so I have to really think hard, if I introduce changes in one corner, how does that affect the rest of the system? So, what are some of those changes? Wind. Wind has seen a tremendous growth. We're now at 60 gigawatts of wind. 60,000 megawatts. That's a lot of megawatts. And you see, it's an exponential growth. Last year alone, we installed 13,000 megawatts of wind. 40% of all the new power plants that came online last year, 42% of those was from wind, the largest number of them. Okay? So the majority of it was really was wind. And if we add up all the other renewables, we add up 55% of all the new installations was from clean power. Okay? So it's tremendous. And worldwide, we have close to 300 gigawatts of wind. So a huge industry. So this is not the small kilowatt-sized turbines anymore. This is big business. It's also spread around the country, with the exception of the southeast, where it's very poor wind resources. We see wind in almost every state. Right? A lot in the Midwest, in the center part where good wind resources are, but also on the East Coast. Illinois has 3,500 megawatts of wind, growing everywhere. But what's one of the problems with wind? Well, sometimes the wind blows and sometimes it does not. Okay? So this is from the Midwest. Okay? This is how wind goes up and wind goes down. And as I add more wind into the system, I have to be able to always balance this out. So if the wind goes up, I have to turn somebody else down. And as the wind goes down, I have to quickly turn something else on. So that's called balancing. I have to balance the supply and demand all the time because I can't store. I don't have an inventory, right? Very little. Okay, I'll show you something later on that we use right now to store a little bit, but we're limited. Okay? So this introduces a lot of challenges. Not when we use a very little wind. Okay? If the wind share is 1%, 2%, this really is not a problem. But we want to get to 20% wind. We want to get to 30, 40% wind. And then we'll throw in solar also. Then this will become an issue. And we'll have to find ways of how to manage that. In addition to the hourly up and downs, all the time going up and down, it also varies by season. Now, when do you think we need most of the electricity? When do we consume the most? During what month? Summer, right? July and August. This is when we run our air conditioners. This is not good because most of the wind just happens to be blowing in April and spring and late in the year. And the lowest amount of wind we get is typically in the summer months. So we have situations where the demand in spring is very low because our air conditioners are not running yet. The wind is blowing a lot, and because of all kinds of constraints in the system, we all of a sudden have too much. Okay? And if we have too much, we actually force the wind turbines to turn off. The wind blows. Okay? Don't get me wrong, the wind blows, but we can't use it. So we actually tell these guys to turn off. We call that curtailing, spilling the wind, curtailing the wind, essentially throwing it away, not using it. And there's quite a bit of that. In 2010 in Texas, they threw away almost 15% of their wind resource. Right? So they're working on it. So that's not a good use of that resource, right? We spend a lot of money building those turbines, and the wind is blowing, and they're not allowed to turn. That's not good. Okay? So that's obviously an issue. Solar, similar. Potential exponential growth. Last year alone, we almost doubled solar PV. You know, we have a little, I don't know how many, 100 kilowatt solar PV panels on site. We're talking lots of PV. So we're at 6.5 gigawatts in the US. Worldwide, though, we have over 100. Germany is the world leader. Germany, the country is the size of the state of Montana, with 1/3 of the population, about 80 million. And they have about 5 times as much solar PV as we have, in a place where the sun shines as much as Alaska. Right? So who here would propose to put 30,000 megawatts of solar PV in Alaska? We wouldn't try to do that, right? We put it in New Mexico, Arizona, Utah, where the sun shines, right? Germany decided to go another way. All right, they realized they don't have enough solar input. Okay? Insolation is low. But still, they wanted to build up an industry, so they did that. Spend a lot of money. Now they're the world leader, so just for comparison. Now, as we invest more and build more, the costs are coming down. So we see a constant drop in solar PV system costs. And of course that is then reinforcing, right? As we ramp up production, the costs come down and it becomes more attractive, and so more people will buy. A lot of this is also driven because some states actually require the utility to buy certain shares of renewables. So the state of Illinois requires ComEd and Ameren to buy a certain fraction of the electricity that they're selling to you from solar. So that drives that too. But similar to wind, solar forecasting is easy. On a day like today, blue sky, no clouds, I can nail that, okay, 100%. Okay, there's no problem. When the clouds move through, then we have a big problem. Then it looks like the blue and the green. On the clear sky day, it looks like the red line. 100%, no uncertainty, forecasting is easy on that day. But on the blue day, big problem. And again, right now with 6.5 gigawatts, it disappears in the noise. 6.5 out of a total of 1,000 gigawatts nationwide. Those 18,000 generators, they add up to 1,000. So it's a very small share. But again, the solar guys, they have a target too. They want 20% solar. Right? So as we add more solar onto the system, we have to be able to deal with that variability on a day like the blue day. And so what does that do to our system? Okay, so here's a way of how we typically operate our power system. Okay? So our demand constantly goes up. I mean, at nighttime, we're all in bed, turning things off. My kids don't, but some kids do. All right, and then we get up, the demand goes up, and it follows this daily cycle, and on weekends, it's a little lower. All right, so and then we use our different technologies. So first, we start running our nuclear power plants flat out 24/7. Then we start loading our coal generators. Again, they run pretty much flat out. And then we use our gas generators, and some of them run flat out 24/7, and others follow the demand a little bit. And then up on top here, if we have hydropower, we really use the hydro resource to follow the demand to balance things out. So this is how we traditionally do it. Okay? Now, let's throw in some wind. So if we have 10% wind, it starts to affect the gas guys, the gas generators. They get used less and differently. They have to change the outputs more frequently, right? They have to go up and down more frequently. And as we go into 20%, it starts hurting the coals. The coals have to turn off sometimes. And as we go to 30%, there'll also be an effect on the nuclear guys. Right? And so you can see, as we introduce more of that resource, the way we used to will be very different than the way we may have to 10 years down the road, 20 years down the road. And we have to be ready for this. Prices. This is the wholesale price of electricity here in the Chicago area. Most of you probably don't pay that. Most of you pay a flat price, one summer price in summer, one in winter, or maybe one year-round, same price. But in reality, on the generation side, on the wholesale side, price of electricity changes every hour. In fact, every 5 minutes. You don't see that. But the guys who buy and sell electricity, they see that. So if you look at this, what's one thing that you notice right away? Huh? There's negatives. So when was the last time you went to Jewel and you bought stuff and they actually gave you cash? Or pulled up at the pump and filled up and the guy gave you $30. Right? Doesn't happen anywhere else. Not that I know. Okay? But with electricity, it happens. Why does it happen? Anyone want to take a guess? Why does this happen? Supply and demand, right? Remember the one thing? We are limited in the way we can store it. No inventory management, right? So we always have to produce as much as we consume. And sometimes there's too much production. As the wind blows and the demand is low, and then there's certain things that I can't turn off. Who cannot turn off? Who cannot go up and down often? Nuclear. Exelon hates this. Okay? And so every time there is an oversupply, I would really like to turn off my nuclear generator, but I can't because it's not designed that way. And in that case, Exelon's forced to pay you to take. All right? So this is, and it changes a lot, right? I mean, we complain if the gasoline price goes up by 10% in a week, right? Everybody complains. 20%, that's an outrage. 20% change up and down in a week, all right? With electricity, we see changes of hundreds of percent within a day. Okay? It's like this, it's the equivalent of you pulling up at the gas station at 5 o'clock after work and you pay $20 a gallon. Or the same day, 3 o'clock a.m., you pull up and they pay you $30 a gallon. That's how fast the price of electricity can change on those markets. So it's a very volatile product, and it's volatile because we can't store it. Okay? And because of this, this is why Exelon recently came out and says, hey, the wind guys are killing us. Came out 16% of the time, one of their generators pays to generate. That's not good business. Here, latest Bloomberg headline from last week, I think, right? So we're starting to hurt some of the traditional generators because of this. And in Germany, with even more solar and wind on their grid, it's already starting to hurt the gas guys, and some of the big utility companies there are already starting to threaten to shut down some of their gas generators. So as we move forward, we really have to think about what does that do to our entire mix, and will we have enough other resources out there to balance out the system? Because if some of these traditional generators become unprofitable and they take them out of the market, it'll affect everyone. And then what else is happening? Gas generation is rapidly gaining on coal. I showed you something earlier, right? I mean, 25% gas, 45% coal. It's actually been much higher 10 years back. So 10 years ago, we generated 3 times as much from coal than from gas. Right now, within 10 years, we're pretty much even. This is unheard of. The electricity industry is not known to be a fast-moving industry. Okay? This is dramatic. Okay? In 10 years, such a huge shift. Why is this happening? Well, because there's a lot of old coal plants out there. Remember, 1,400 of them. Some of them were built 50, 60, 70, 80 years ago, right? Pretty dirty, inefficient. And so there's EPA that requires them to upgrade their pollution control equipment, and some of them are saying, well, it's just too expensive. So rather than upgrading them, I shut them down. I retire them. So we've had already huge numbers of retirements over the last several years, and there's expectations that there'll be even more of them being retired and taken off grid. And so this trend is likely going to continue. What's also been happening is that our domestic natural gas production has gone up, particularly in this window. So if you look at the green line, that has really jumped a lot over the last 5, 6 years or so. What's driving that? Shale gas. Shale gas is being produced in the south, in the east, in the northwest. There's pockets where we produce this new kind of resource. It's an unconventional natural gas that we produce, and we introduce this into the system. So now, in the meantime, over 30%, over 1/3 of our natural gas comes from those unconventional resources. And so what that leads to is, the recession helped a little bit too, but what it's really led to is a massive drop in natural gas price. From 2007, 2008, 2009, it dropped to almost, actually at one point below 2. And it also lowered our outlook. We think because of all these resources that we see coming online, we think natural gas prices will remain low, will remain lower than what we thought just 2, 3 years ago. Now, what that does is, last time you checked your NICOR bill or your bill from People's Gas, you should have seen a lower bill. My bill is much lower than it used to be. So this is sort of like the change, right? I mean, so massive drop here, right? From 1 to 2.3. So this winter, you should have paid a lot less for your natural gas than what you paid just a few years ago. Well, and also it helped you in your electricity bill. Again, these market prices you may have not paid in the past because you needed a smart meter to take advantage of those low market prices. But probably most of you live in a town that signed an aggregation plan. There's about 250 communities in Illinois that signed aggregation plans. They switched away from ComEd and signed a contract with some supplier and led to an average 25% savings for all the people that live in those townships. Lamont, Darien, Downers Grove, you name it. They all signed these plans. And you have these savings because of all these other things that are happening. Right? So you actually see a direct benefit of that. And lastly, really, something that's really gone unnoticed is, again, recession in combination with much more use of natural gas, our national carbon emissions keep coming down. All right? And we're almost reaching 1990 levels again. And guess what? We never signed the Kyoto Agreement. All right? And we may be the only country that actually will be able to meet those requirements. Okay? Although we never signed on to it. Okay? And all because of this. Okay? So there's huge benefits to this, right? There's downsides too. And of course there's concerns, right? This is just from this Sunday, I think, in the paper. There's environmental concerns with the extraction of that resource, and we have to address those. And there's concerns too, okay, can we continually extract so much natural gas using that technology from the ground? How quickly this will be depleted and what the cost implications are. So looking forward, we don't know. There's very ambitious forecasts that say we could be energy independent 10 years from now at the latest because of all that resource. Now, whether this play out, who knows? I'm not a geologist, I'm not an expert, but we have to address some of these cost and environmental concerns. And Illinois is in the midst of actually writing the rules and regulations for this industry, if we want to allow in the southern part of the state shale gas extraction. Smart meters. We have 150 million meters out there right now. We're replaced a little less than 40 million by now. This is the 36 is a little outdated. So it's about 40 million households that now have smart meters. Okay? And the goal is by 2015 to have about 65 million replaced. Part of that is done through recovery stimulus funding and state-funded programs. Okay? But the utilities are going out there replacing those meters, the meter at your place. Naperville replaced them all, right? Why do we do that? Well, because this is the way we consume electricity. Earlier we said we consume most of it in summer, and you can see it, right? I mean, in summer it spikes, but it's really very volatile too, right? It goes up and down all the time. And if you don't have inventory to use this, to balance this fluctuating demand, it's really hard to do that, right? Because that's why prices are volatile, because your demand is volatile and you have no storage to speak of. And you know, we're working with a demand that fluctuates from the lowest to the highest by a factor of 3. And we don't have storage. All right? So that's the challenge that we deal with. And so if we now can provide some incentive to the consumers to change the way they consume electricity, instead of turning on your air conditioner at 3 o'clock in the afternoon or 5 o'clock in the afternoon, you turn it on at 10 or 11 or midnight. And you shift your demand. Then this will balance out because we can cut off some of those peak hour demands. And that will make it easier for us to manage the system. This will make it more efficient to run the system, and this will make it more cost effective, and we can pass those savings on to you, and again, you will benefit through a lower bill. Now, each consumer has a different way of consuming electricity, right? So, I mean, households typically have this thing about, you know, regular single-family home, low at night, high during the later afternoon. Large consumers are much flatter. Think of Argonne. Think of this facility, right? I mean, about 20 megawatts to run our APS. We don't turn it on and off just because the price of electricity changes from 1 hour to the next. They'd shoot us, right? Same with a supercomputer, right? Rick Stevens would shoot me if I'd say, hey, turn it off because the price of electricity just spiked, right? We don't want to do that. We don't turn things on and off, okay, just because of this. So some consumers can change the way they consume, others may not. Here's what I have done in my house. This is actually after I installed my smart meter. This is how I consume. That's the blue line. And the red bars are the prices that I paid. And what you see is often the blue line is still high when the prices are high, and the blue line is low when the prices are low, and that's not good. I want to consume a lot when the prices are high, when the prices are low, And I don't want to consume much when the prices go up. And so after fiddling around with all kinds of settings in my house, you know, going crazy around, running around, I was able to do that. I was able to shift. Okay? And now I consume the highest when the price is the lowest. Okay? And my demand is really down when the price is high. So I can take advantage of that. Okay? It takes a little bit of work, but I can save money by doing that. How much? In the meantime, as of actually last month, it's $2,500. I save $500 on average per year on my electricity bill by doing that. $500 a year. That's not bad, right? Comes at a price though, okay? So for one thing, on a hot, balmy August morning, when you wake up in my house, this is how it feels. Because the air conditioner runs essentially from midnight to 8 a.m. full time, full power. Set point is about 55. Okay? Freezing cold, okay? Then it turns off, and it never kicks on until 6 o'clock in the afternoon, so guess what it feels like at 4 o'clock? Okay? And this is what my dog thinks of the whole thing. And I'm not allowed to tell you what my wife thinks of this because I can't put that in print. Okay? But you can save, right? Now, on top of that, now imagine I had an electric car. Like one of these nice things, right? That we just had a great time showing off, right? So what does that do? And could I take advantage of this, these low prices here, negative prices? What if I charge my vehicle then? Perfect, right? They actually pay me to charge my battery in my vehicle, all right? So there's potential, you know. But I also have to make sure I provide the right incentive, because if you plug it in once you come home at 3 o'clock in the afternoon or 4 or 5, when the demand is still high and the grid is strained in somewhere, then you might cause more of a problem. And I don't want you to do that. So we really need to understand how people will use these electric vehicles, how they will drive them, how they will use them, and how they will charge them. Okay? It has a big impact. So here's a couple of things that we do to address some of these challenges, right? So we work for DOE's wind office, solar office, hydro, the water power program, and then of course the electricity office. And really this is a multi-division, multi-ALD-ship of effort. I mean, so we work a lot with EVS and with MCS, DIS, ES, so there's a lot of divisions involved in this, okay? Not just us, okay? Because this is a big thing. And ALCF too, the Leadership Computing Facility, because we need to be able to scale up our models, and you just can't run them on a desktop anymore, because the systems get much more complex and large. Okay, so in hydropower, I said hydropower has been a no-no for many years, but we have a lot of these dams around. This is the Glen Canyon Dam, one that Tom Viselko, who sits in the back, he's been making his career sort of studying this thing. This is essentially a big battery, right? We don't store electricity chemically. We store it in the form of water behind that wall. And it's up to us when we want to use it, when we want to release the water. And so really one thing to do is, and what we've got in charge from DOE is say, all right, can we use the water behind this wall more efficiently? Can we do some kind of grand optimization to say, all right, without even adding anything onto it, can we get more power out of it, and can we get more value out of it? All right? And so this is a big activity now. Okay? So this is one thing that DOE wants to focus on, optimizing the current existing hydropower dams that we have all over the country. Okay? And then there's another one. Can we upgrade the generators? Can we build generators at dams where we have the dam already but not a power generator? And can we build new hydropower? That's a big shift in DOE's thinking. For the last, I don't know what, 20 years I've been here, building new hydropower was a no-no. Now it's all of a sudden on the table. Okay? And so we're big. We're actually the lead lab in that regard. And we just last year got an award for $2 million to look at pumped storage. What's pumped storage? Pumped storage is essentially 2 buckets of water, one at the bottom, one at the top of the hill. And you charge the battery at night by pumping up the water, okay, up in the upper reservoir. And you discharge the battery during the day by letting the water run down and through a turbine to generate power. So simple way, a big battery, okay? And they're all over. They're not around here much, not in Illinois, but we have some right here on the Great Lakes in Michigan, 1,900 megawatts. It's huge. So you have the artificial reservoir on the top, but this is the lake. And they just pump the water up at night here, let it run down during the day to generate power. And you try to capture the value of that difference. Prices are high during the day, prices are low during the night, and so you can make money off of that. And you can use this to balance that variability of solar and wind. Another way, something else that we can do is, of course, we can get better forecasting. If I could just perfectly forecast how much wind I'm going to get and how much solar I'm going to get, not a problem, right? Then I can get ready for it. But really, there's uncertainty around that, right? I mean, because all you have to do is listen to Tom Skilling's weather forecast for this weekend. How much are you going to trust him? If you plan a party, you know, outdoor party, you're going to trust him? If he says there's an 80% chance of sunshine, right? So we want to improve that confidence in that forecast. Now, one thing we've teamed up last year is with IBM. IBM, we tapped into their Watson, and we renamed it into Watson. This is really all we had to do to win that proposal. Having IBM and having a smart name, okay? We really didn't have to write a 20-page proposal. And basically use the machine learning, that big brain in that machine, to see if we can come up with better forecasting of solar power. And we have a whole bunch of partners. This is a large team. Argonne is IBM is the largest. They're leading. We're the second largest partner, and then we have a whole bunch of others. And we will be testing this with several different utilities across the country, from the East Coast to the West Coast. So this is an exciting project. They just had the kickoff meeting last week. So it's just getting on the way. So we're very excited about this one. Wind. This is what probably some of you think of wind, right? This is gone, okay? We're no longer thinking wind this way. This is more like what you're looking at, okay? I mean, here, notice the guy sitting right up here, right? I mean, this is about 200 feet going down, okay? This is probably not meeting the Argonne safety plan. I don't know. And notice the rotor down here, right? So this is the standard wind turbine these days generates 1.5 megawatts to 2 megawatts per turbine. The largest wind farms, meaning a collection of turbines, has 900 megawatts. That's huge. Okay? So we're talking hundreds of turbines in one wind farm. Here's just a size comparison, right? So the largest land-based turbine is about 6 megawatts right now. You know, 440 feet up all the way to the tower. Okay, huge. So, but if we want to go beyond 6 megawatts, if we're going to go 10, 15, 20 megawatts, then we're going to run into problems with the weight and the size of the generator. So last year we teamed up. And this is actually the physics division who's doing most of the work here, to team up with industry partners to develop the next generation turbine technology. And so here we're proposing, and we're actually building a small scale model now this year for a fully superconducting drivetrain. And why Argonne? Because we have a superconducting linear accelerator Atlas here. And so we were able to bring that capability to the table. And so actually next year, we'll be doing a test on a small scale model. It's about 3 feet long and 1 foot in diameter to tap into the cryogenic, the refrigerator here at Atlas, to test how that thing performs under operating conditions. This is a pretty exciting project. And DOE only made two awards. Okay? So we're part of one of them. And they have commitments to actually move this all the way to demonstration stage, okay? Small-scale pilots out in the field. So this is pretty exciting if we can continue to show that we can do this. Very exciting. Another one that we're working on is being able to handle the uncertainty. As I said, we never will be able to fully 100% forecast wind or solar or the weather for your party this weekend. So we have to come up with some kind of models that can handle that. We call those stochastic models. Can I give the operator who makes sure that the power always stays on, can I give them more information about the uncertainty of that wind and help them make better decisions? And that's a big thing too. And by developing those models, we show that we actually can save money by doing that. And we can show also the benefits of a smart grid. If we connect you up with a smart meter and allow you to respond to some signal that says, hey, right now I have an oversupply of wind, why didn't you turn things on? Or I have a shortage because the wind is dying down, why didn't you turn things off? If we can make that work, we can show that we have to invest less and we save money. We have to build fewer power plants. And we can run our existing power plants more efficiently, so the cost compared to this is lower. So we have cost savings, and we can clearly show those benefits. We also look at electric vehicles, right? So what can electric vehicles do to help us out in that regard? Or are they a problem? Okay, if you charge at the wrong time. If you charge at nighttime, that might be okay, because the demand right here is already down. So if you charge the green ones at nighttime, the grid can easily handle that. If you charge as you come home, and this is sort of like a distribution of how people come home, arrive at home. So if you just drive into your garage and start charging as you come home, we might have a problem, because then your demand is the highest when the system demand is still high. And that might cause an additional strain on the system. And so we need to know that. And we're working with ComEd to actually go down into micro level. We're teaming up with ES, the TRAC Center, to do micro simulation of the Chicago metropolitan area, using some data from ComEd to see is there problems somewhere in the Chicago area. This is another one, okay? So if I could find out, if I could identify places in the country that have concentrated amounts of clean resources, I could then provide incentives to developers to say, hey, focus your resource development funds, your investment funds into those pockets, okay? And I'll provide incentives to you to do that. And I make sure that you can actually ship that resource to the consumers, okay? They've tried to do that in the West. They've tried to do that in the East. And nobody has tried it so far in the West and in Texas, and nobody has done this in the East yet. And the East is more complicated. More states, less public land, lots more stakeholders involved. It gets very tricky. And so it's been sort of just too complicated. And so, but DOE has started this. This is a project that EVS is working together with DIS to sort of develop this online tool that allows stakeholders to go through this process. And the next step is really, and we sort of think that we might take this to the next level, where we can then actually use this tool to identify in which parts of the countries do we need to build more transmission lines, more pipelines, ways to ship things. We call those energy corridors. Now, if we do this, then that gets a lot more complicated. And so for that, we actually need to have more efficient models. And so one project that MCS and ALCF is working on is new methods, new tools, more efficient tools, something that we can scale up, something that would allow us to simulate this entire system and possibly even the entire country. We don't have a model like this right now. It doesn't exist. Okay? It stretches all the capabilities that we have right now. But what if we had? Can we bring our math and computing sciences capabilities to the table to allow us to scale up, develop methodologies and tools to allow us to scale up to that level so that we can simulate and analyze the entire grid, okay, all together in one tool. Okay? And so MCS just recently got an award from the Office of Science that's particularly geared towards developing advanced methods, algorithms, things that allow us to take advantage of the petaflop machine, 10 petaflop machine Myra, and maybe get us ready to go to the next level, exascale computing, okay, so that we can tap into that. Because what we do think is to be able to handle all this, we really need a lot more computing resources. So this is something really that is, again, MCS, the Leadership Computing Facility, DIS, and other divisions are all involved in working for the Office of Science and the Office of Electricity to come up, to get the tools ready, to get the tools in place. And there's actually one great example of where the Office of Science coordinates with the Office of Electricity to work towards a greater goal, which really was amazing. It's the first time I've seen that happening. Okay? So very excited about this one. And then lastly, we're pushing the boundaries, right? I mean, so we're running more and more into situations where people just don't want the turbines anymore. Okay? Some people like turbines, wind turbines, others don't like them. Right? And so there's many hundreds of thousands of megawatts of potential wind farm developments that are held up by somebody opposing it for one reason or another. Right? And the other problem with land-based wind is the best wind resources are Montana, Wyoming, North Dakota, South Dakota, I could go down the list. How many people live in those places? Not a lot. So the best resource is really where we don't really have a lot of demand for it. And so often what we run into this problem is that we don't have the transmission to move the power from those good resource locations to where we need it. Now, we have a lot of shoreline on the West Coast and the East Coast as well as on the Great Lakes, and that resource is right there where we need it, if we could somehow tap into it. We don't have any turbine in the US in the water right now. There's no such thing right now. They have some in Europe, okay, and DOE has high hopes and big initiatives to sort of tap into this, okay, to build something like this. And again, they're gigantic. And for this particular application, it's really they're looking at 10, 15 megawatt individual turbine sizes. Okay? So as we go into that, and I said there's a resource of 4,000 gigawatts. If we could put turbines everywhere where we think they could go, 4,000 gigawatts. In the Great Lakes, 740. That's almost as much as what we have right now. So it's huge, okay, if we can tap into it. But the problem is we don't really understand the resource. We don't really have any meteorological towers out in the ocean where we collect data, know how the wind blows. It just it's not out there, right? So we need to really get a better understanding of that resource. And this is where EVS comes in, because EVS is, through the Office of Science, has the ARM facility. That's a mobile facility that gets deployed all over the world. And I think this has a big potential for Argonne to play a role, assist DOE to get a better understanding of that resource. We don't really know how much it fluctuates from day to day. We don't know how much it varies from hour to hour. We don't really know how good the wind is in those locations. And there's a big push to get more instrumentation out in the oceans to get a better understanding of that. And I think Argonne, as a whole, multiple divisions can play a role in this. We just had DOE, the Wind Office, the program manager actually here at the lab last week for a day, together with GE Global Research. They're also interested in this. So this is something that might happen in the next year or so. And this is the last one that actually, that was the reason why GE came, is because we have different models modeling at different scales. So we have the larger climate models, they work on the sort of this scale, large scale. Then we have the weather forecasters, they work what we call a mesoscale, regional levels. But really for me to figure out how much wind my turbine produces, or could produce in a potential new location, I need to go down to like a very low resolution, 1 mile by 1 mile. And I really need to be able to figure out, okay, so what does that mean for each individual turbine? And what's the turbulence effects of one turbine being lined up to the next one? And how is that wind turbine, by moving the rotor around, how does it affect the wind turbine behind it? The wake effects, the additional turbulences that these things create. And so what we have is, we need to actually look at the turbine level. And so we've started already. I don't know if that will work. So this is something that Julia Pete and Paul Fisher have developed using Argonne's CFD, computational fluid dynamics capabilities, on our supercomputer to start simulating some of this. Okay? But what we really want to be able to do is not just 2 turbines. We really want to model 100 turbines. Okay? And this, of course, again, is where we need the big machines. Okay? And this is something that really DOE has sort of declared as a high priority, because we really don't understand what these things are. This looks nice, looks pretty, but it's not validated at all, because we don't really have the data to validate that. And so DOE is probably starting a $30 million initiative to start doing wind tunnel testing, data collection in the field at multiple levels, and develop the new tools that allow us to understand that. And Argonne has atmospheric sciences capabilities, the guys that deploy the mobile facilities and the stationary facilities, all the ARM work that's funded by the Office of Science. The optimization, you could say, all right, so how do I actually optimize the location of 200 turbines? How should I place them? No one's really doing that right now. It's seat of the pants. We have a lot of people that work in optimization that can be brought into this. And so I see this as a really huge opportunity for many divisions across the lab to help DOE out to come up with better tools to estimate what a wind farm can produce, What are the impacts of one turbine on the other? That turbulence, does that affect the lifetime of the turbines? If there's additional turbulence? How does it affect the lifetime? Because many times what we see is the turbines, they don't last as long as they're saying they should. There's no turbine that lasts 20 years. They break all before that. Mostly because we don't understand the dynamic loading on those turbines, on those blades, on those rotors, on those generators. That's a huge gap. So, just on time, remember from the beginning? Just in case you forgot, lots of changes. Lots of changes both on the supply side, wind, solar, coal retirements, lots of natural gas coming on, lots of changes on the consumer side, on the demand side, electric vehicles changing the picture, smart meters changing the way you consume electricity, and they all play together and in a way that we don't really have the tools right now to fully understand. And I think this really opens up the door for us to have a whole range of research opportunities that are being funded as we speak. Again, the Wind Office, they are putting $30 million on the table later this year to get a better understanding of this. The Office of Electricity is working together with the Office of Science to get better tools in place, long-term commitment, because this is not something that we can develop in 6 months. This is really a 4, 5, 6 year endeavor. So I think there's a lot of interesting research that allows, that is really, we can do, that allows us to do that because of all these things that are happening. And so I think this is exciting for us. This is growing already a lot, and I just look forward to a lot more growth in this and engaging as many people as we can across different divisions and across different capabilities. So with this, I'll be more than happy to answer questions.
So, questions?
No questions? Yeah, you talked a lot about the supply side, renewables, shale gas.
Yeah.
You talked a lot about the demand side changing. Can you talk a little bit about the distribution side? Or, I mean, you mentioned the distribution.
Yeah.
But, you know, a little bit about what changes we can expect there to handle the changes on the end.
Oh, okay, so on the distribution side, what changes can we expect? So, substations, they're pretty dumb right now. And so what we're working on is actually come up with smart substations. There's a pilot in the Chicago area, ComEd has one of those, working on a smart substation that will be able to, in the future, to automatically reroute power depending on what happens on the different lines, if you will. Okay? Right now, the standard substations can't do that. Okay? Right now, if a storm moves in and the power goes out on your block, well, that's in my case, I lose power, and my neighbors across the street who are on a different, what we call feeder, lights are on. Now, how do they find out right now that that's the case? How do they find out that my power is off, I lost power, and the guy across the street has power? They only find out once I start calling. They don't know that. Right? ComEd does not know that until you call. You pick up the phone and actually physically make the phone call and say, hey, I'm out of power. And they say, oh, okay, all right, 5333 Blodgett, let's send a truck out. You know, and I might be in line. You know, I might be the 5,000 caller, and it might take 3 days for them to show up, right? In the future, on the distribution side, this will all be automatically. So send to ComEd. So they will know who's out of power, who's not, how can I reroute the power to quickly fix it up, and how can I dispatch my crews the most efficiently to bring on the most people as fast as I can. So all of those changes will benefit us indirectly because it makes the system smarter. Okay, and then the response time to emergencies, and most of those emergencies are happening on the distribution side where we lose power, storms and other things. That, I think, will be the biggest benefit, I think, that we will see. And so that's where I see changes there.
Other questions?
Yeah.
What is sort of the average cost of wind power today?
Okay, so the average cost of wind power, so So DOE distinguishes between land-based and offshore, okay? And so we keep track of those, and the costs have come down, okay? So in terms of cost, depends on what metric you want to hear. So there is the investment cost, that's dollars per kilowatt installed capacity. So wind roughly is about $2,000 per kilowatt installed capacity, okay? And but there's no fuel cost, right? Because wind is free. So if I levelize that over supposedly a 20-year lifetime, then per kilowatt hour, the price roughly is about 8 cents a kilowatt hour right now for land-based on average. We really want to bring it down to 6 and below. Okay, so that's DOE's target for land-based wind, to bring it down to 6 or below, because they feel like this is really where it can compete without any government help. Because the government is helping out with 2.2 cents a kilowatt hour right now. It's called the production tax credit. So I have to shave that still off. So there's still work to be done on land-based. Offshore, we're way off. Okay? Offshore right now, that's estimated, because we don't really have any turbine in the water right now, we're estimating about 25 cents a kilowatt hour right now. So we have to bring that way, 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 way down. And that's why they issued a $150 million solicitation last year to actually get turbines in the water. So they want to get 2 or 3 demonstration plants, maybe 2 or 3 turbines out and want to test it out to see, can we manage that? What can we do to bring those costs down? So that's how it compares.
Other questions?
Yeah.
There's been a lot of talk recently about DC power transmission versus AC power.
Yeah.
Can you address the difference in efficiencies, and is that going to be a trend?
Okay, so for DC, it's typically what you want to do is you want to have a lot of power and over long distances, and then it's more efficient, it's more cost effective too. So I was just at a conference at the workshop 2 weeks ago, talking to somebody from Manitoba. They're actually in the process of building 2,500 megawatts of hydropower, way up, okay, in the Northern Territories. And that's like 1,500 miles away from anywhere where they need that power. And for that, they're using DC, direct current, high voltage direct current transmission lines. Over distances like that, that's where it makes a difference, because per kilowatt hour or megawatt hour, the cost is then lower. So you see a lot of HVDC line investments in China. China is building huge amounts of those, okay? Because it's a big country. They're starting from scratch, so they don't have the big build-up system that we have over 100 years. And so what they're doing over long distance, they're pretty much only building DC lines. So if you talk long distances, lots of power, 1,000 megawatts or more, that's where DC lines become economic. Oh yeah, right here. Okay, yeah.
I was just going to ask about cybersecurity.
Cybersecurity, yes. Now imagine 150 million meters with a connection possibly through your network, in-home network. So that's 150 million entry points into the system, okay? Now, okay, so imagine you're wireless at home, right? So we're not concerned so much about some foreign entity going in there, but it could be your neighbor's kid who is a computer wizard trying to screw around with your settings and messing up the system, okay? So that could be a concern. But 150 million smart meters that I can address, and then all the substations where I put computerized now, it is a concern, and DOE has a big initiative in cybersecurity. And from the Office of Electricity's perspective, addressing cybersecurity concerns as we move towards a smarter grid is probably priority number 1. Because it makes it vulnerable. I mean, because it provides more entry points into the system.
So a question
in the way back, I think.
Hey, Guenter, nice presentation so far. Follow-up question?
So far, okay, good. Only one more minute to mess it up.
But I have one question. It's a follow-up to the DC AC question.
Yeah.
What kind of percent line loss inefficiency do you see with DC versus AC?
Okay, where's my electricity guys? Anybody want to take that? Okay, on the AC line, I think it's usually about 5%, 3%, 5%. On DC lines over longer distances, it's less than that. But every percent makes a difference.
Thank you.
We're talking lots of megawatt hours, right? Or gigawatt hours that are transferred.
Okay.
So I'm not the electrical engineer, but I think I got a nod, roughly.
So can I ask a question over
Yes.
this way?
Sure, yes.
Yeah, protect the prerogative. So I wouldn't I want to talk about real-time pricing for a second. I
Yeah.
wouldn't characterize you as a typical consumer.
Say that
I
again?
wouldn't characterize you as a typical consumer taking advantage of real-time pricing.
Yeah.
So that was a great example.
Yeah.
But the utilities, put yourself in ComEd's shoes.
Yes.
In order to take advantage of this, they
Yes.
have a huge education
Yes.
challenge in front of them. How
Yes.
would you embark on that?
Okay, so educating the consumer about the benefits of the smart grid it lags behind, way behind. Okay, most people really don't care. They don't want to know. They don't want to read. I mean, I spend a lot of time reading up on this, right? And I do my little experiment. And not everybody has a wife as tolerant as me, I suppose, experimenting around with all this stuff, right? So I have to admit, you know, my family is still willing to cooperate with me 5 years into it, but I might get the boot soon, okay? So most people spend $100 on their electricity bill. The average bill is $100. So for me to convince you to save on average 20%, that's $20 a month. That's a challenge, okay? So for people to make you care, okay? So we haven't figured out yet how really to educate the consumer. I was at a ComEd education workshop, okay, like in Orland Park, and 6 people showed up, okay? And I was one of them. And all they asked about, how much does that impact my bill? And all they talked about is how great the grid is to make it more efficient, to save carbon. Nobody cared about that. Okay? I mean, so if I can effectively communicate to you that you get benefits in out of your pocket and lower your expenses, then I have a chance. But again, the business case is hard because I can tell you probably that you can save on average $20 a month. And how important is that to you? So on the outreach, it's far behind. We have 40 million meters out there right now. Only less than 1% of those smart meters right now actually receive some kind of price signal. All the other meters they're just collecting data, but they're not doing much. Okay? So that's a challenge, all right, on consumer education. And ComEd hasn't, as far as I don't know if anyone is here, but I think they still have a long ways to go in terms of figuring, and not just ComEd, everyone, really.
Okay, one more question, I think,
Yeah,
and we'll have to
okay.
break.
Actually, my friends from California can speak about education where they're paying 80 cents per kilowatt hour during peak hours. So they get educated real fast with regards to time of use.
That's right. So, but nobody here pays 80 cents a kilowatt hour.
Right, but
Right,
in
so
California they have
so
to.
once you roll those out and then you educate the consumer, then I think it's easier, right? But I mean, but California has been at it for a while.
Absolutely.
Yeah.
But with the advent of distributed generation now, and one of the alternatives to controlling demand is the increase of energy storage. And could you
Yes.
just maybe
Yes.
speak a little bit on the developments of utility-grade energy storage and how that's going to impact the continued development of distributed generation?
Okay, so if I had another 45 minutes, I could probably do that. So yes, I mean, you know, the points I made repeatedly, we don't, you know, we're challenged by the fact that we can't store it a lot. I mean, a lot, right? I mean, I have my phone, everybody has a phone, we can store electricity. But if you do the math, it's really, really, really expensive, okay? So on a large-scale grid scale, it is a challenge, okay? And so the technologies that we have right now, 22,000 megawatts of pumped storage, that is by far the most popular way of storing electricity right now. But there's others, and so there's talks that we give. In fact, we have a storage workshop Wednesday, Thursday, right? Isn't that it? Tomorrow? Yeah, tomorrow and... Yeah, tomorrow is Wednesday, Thursday. So with IIT, there's a 2-day workshop on energy storage just for that purpose. So there's different technologies. There's obviously compressed air. So we use underground caverns, push air down there, compress it, and then use it during the day to run a turbine at a higher efficiency. There's flywheels, there's capacitors. I mean, there's a whole range of new technologies that are being explored. Superconducting magnets, it's a whole gamut. But the point is, they're all far too expensive right now for commercial applications. And the only thing that we can do right now at a commercial scale is 2 buckets of water, one on top of the hill, one at the bottom. Okay? But we are limited in terms of how many locations we have for that. And we don't want those things in all of those locations where we could build them. Right? So we're location constrained. So we're looking for alternatives. And Argonne's actually, as part of the hub, is looking mostly at batteries for vehicles, but also at flow batteries. So flow batteries is another technology that can be used at a larger scale. And so that is actually being investigated as part of the hub. But again, storage is a big topic. I couldn't do it justice in a minute. But again, if you're interested, D120, Building 203, tomorrow and on Thursday is a two-day storage workshop.
Okay, I think we're going to need to stop it there. I want to thank Guenter and Dick for a fantastic talk.